Thank you, Professor, for your kind introduction. Uh, Hi, everyone. Good afternoon. My name is Sudhi MAHADEVAN. Uh, I'm doing my third year PhD under the supervision of Dr. Stephen Sang. I'm very happy to share some of my recent research results on investigating the effect of molecular packing on CT characteristics of Y6 and ITAC non-fluorine acceptors using electro-absorption spectroscopy. And this is my outline. First, I would like to give a small introduction on the development of organic solar cell and also the non-fluorine acceptors. Then we will going to see how to probe these excitonic properties of Y6 and ITIC using electro-absorption spectroscopy. Then we will look into how we can control the molecular packing and understand the intermolecular charge transfer properties. Then the conclusion part. So as we all know that in 1985, Dr. C.W. Tang introduced the organic photovoltaic cell using CPC and Perlin derivatives. And in 1995, Alan Healy group introduced donor acceptor heterojunctions. We all are quite familiar with the excitonic effect in organic photovoltaics, right? The formation of Frankel excitons, that is the strong Coulombic strong Coulombic binding between the electron and the hole actually can affect the exciton dissociation efficiency and increase the voltage loss in organic solar cells. And so how to overcome this excitonic effect? So that's why we can implement different strategies to enhance this exciton dissociation efficiency. We can use novel materials with good excitonal properties and physical mechanisms behind effective charge transfer. And coming to the acceptor materials, we started with PCBM in 1995, and due to the limitations in optical absorption and the large voltage loss, in 2015, people introduced ITIC. It is a ADA molecular structure material. And we know that for the last 6 to 7 years, the PCE of organic solar cell is now approaching 20%. It is because of the development of non-fluorine acceptor called Y6. Compared to fluorine acceptors, non-fluorine acceptors they can extend the optical absorption to the non-infrared region. They have better energy alignment with the donor materials and reduce photo voltage loss. And with the popular donor material called PM6, Y6 shows efficient exciton dissociation, negligible geminate recombination, and also excellent charge extraction properties. But there is a question, why Y6? Why Y6 is the best non-fluorine acceptor we have, and how? The solution is we can investigate the charge transfer properties of Y6. And Y6 was introduced in 2019, and then from that time itself, people already started to investigate what are the fundamental physical mechanisms behind the excellent performance of Y6 non-fluorine acceptors. Like it has A-DA molecular structure, so it can enhance the intermolecular electrostatic interactions. It has pi-pi molecular packing from GVAX. Delocalization of electron wave functions. It was explained in Professor Ip's paper in 2020, the ISOCOM paper. Then large quadrupole moment of Y6. It can create an electrostatic potential for efficient charge separation. Then Y6 have long exciton lifetime around 1 nanosecond. And we are more concentrating to understand the intra and intramolecular interactions. That's why we were curious to know how this molecular packing influence the CT characteristics of Y6, or does the Y6 molecule itself has CT property? But the main challenge was most of these studies were based on theoretical simulation like DFT or molecular dynamic simulations, limited experimental investigation. That's why we wanted to probe the exogenous properties of Y6 and ITIC by means of electro-absorption spectroscopy. And this is the setup that we are using in our lab. We are using a transmission mode, and the sample is placed in the cryostat under vacuum around 10 raised to minus 5 millibar. And we have a silicon photodetector to detect the signal, current preamplifier to amplify the detected signal by adjusting the gain and sensitivity, and low-gain amplifier to adjust analyze the signal. And we are applying a voltage to the sample using a function generator. Okay, why we are applying this voltage to the sample? Yeah, this is electro-absorption spectroscopy. Electro-absorption spectroscopy is a powerful technique to characterize the exciton state of properties of energy state under electric field by monitoring the changes in optical absorption. What happens to the optical absorption under electric field? So it works under Stark effect. And in this figure, you can see when we apply electric field, the energy state will shift by a parameter delta E under electric field, which depends on the changes in dipole moment and change in polarizability between the excited and the ground states. And this is an example of we did EA spectroscopy on PCDBT, the conjugated polymer. And how to analyze the signal? That means if the EA spectra matches with the first derivative of device absorbance, that indicates that it is more Frankel excitons. And if it is second derivative, then that means they are more CT type, like CT excitons. And we can see this example. This red curve shows the second harmonic EA spectra of PCDBT, and it matches more to the black curve. That indicates that PCDBT has more Frankel excitons. And this is the equation of the EA spectra that we have derived. Delta T by T is the EA signal. Delta T means it is the change in transmittance with and without electric field, and T is the transmittance without electric field. And this is the voltage we are applying, VAC, and D is the thickness, that's the electric field. So, and delta P, the change in the polarizability contributes to the first derivative, and delta U, that is the change in dipole moment, contributes to the second derivative. So that actually makes sense, right? Well, when we are expecting a strong CT, the change in dipole moment will be more. Like if the electron and hole are separated by a large distance, then it will be easy for separation. And in general, we can say that these excitonic properties are determined by the relative contribution of first and second derivatives to the EA spectrum. Then we are going to see how we can control the molecular packing and understand more about the intermolecular charge transfer characteristics. For that, we did UV visible absorption of Y6 and ITAC non-fluorescent acceptors in thin film and solution. And you can see there's a redshift for Y6 and also ITIC, which gives us the primary evidence that Y6 and ITAC shows molecular packing on thin films. That means like in solution, they will be more dispersed, right? Then there is a question like how we can control the molecular packing on solid state thin films, like how we can disperse these molecules by controlling the molecular packing on thin films. That was the main challenge for us. And we used the dilution effect. We used a polymer in order to disperse this Y6 in the polymer matrix. And you can see there is a, when we increasing the concentration of Y6 in the polymer matrix, there is a gradual redshift, it is shown. And there is also a spectral broadening. There is also a small blue shift also we can see. We used a similar approach to ITAC as well, and it worked. ITAC also shows redshift when we increase the concentration of ITAC in the polymer matrix. So what is happening there? It is based on Cash's theory. This redshift and blue shift are actually caused by the formation of different dimers. J-type and X-type dimers. The J-type dimers, if the Y6 molecules have more end-to-end interactions, then it will form J-type dimers, which shows a redshift. And if the Y6 molecules have more planar interaction, like face-to-face interaction, then it forms X-type dimers, and it shows a blue shift. And from this figure, we can see Y6 have more redshift and spectral broadening compared to ITIC. That indicates that Y6 has strong molecular packing compared to ITIC. That it's shown by different dimer configurations compared to ITIC. So now the samples are ready. We can go to the EA results, and this is the most important results that we have got during this research study. This indicates, so we can see the increased concentration of Y6 in the polymer. Like this is 10% Y6, 15%, 40%, and this is 100%. And we are more concentrated on the S1 state because S1 state is more responsible for the charge transfer and the excited dissociation and recombination losses. In 10%, 15/6, you can see this is a combination of first and second derivative, right? It is not completely first or second derivative, it is a combination. And when we increasing the concentration of Y6, you can see it is more matching to the second derivative. In pure Y6, it is purely second derivative. We can see the negativity, it is more second derivative. That indicates that when we are increasing the concentration of Y6 in the polymer matrix, the charge transfer property is increasing. And also one more thing we can see, the theoretical transport band gap of Y6 is around 2 electron volt. That is also in all these concentrations at 2 electron volt, it is becoming more second derivative. The red curve matches with the blue one. That means it is becoming more charge transfer. So from this result, experimental results also we can get like transport band gap of Y6 is equal to around 2 electron volt. Then what is happening here? When we are increasing the concentration of Y6 in the polymer matrix, the intermolecular electrostatic interactions are getting larger, which further enhance the electron delocalization. And thus the S1 state becoming more CT type. So here we can say that Y6 has strong molecular strong CT property because of its molecular packing. And one more thing we can say that exciton binding energy. Normally we will define exciton binding energy as the energy difference between optical band gap and the transport band gap. So this is S1 state around 1.6, and this is a transport band gap. So we can expect like around 400 milli-electron volt as the binding energy for the dispersed one. But when we are increasing the concentration, here the S1 state itself is becoming more CT. So we can say that it is around 100 to 200 milli-electron volt. Then that is the reason why we have from literature the exciton binding energy of Y6 is around 100 to 150 milli-electron volt, which we also get the similar thing here. So as a reliable reference, we also did the same study on ITIC. And interestingly, what we have observed is that this is 10% ITIC and this is 100% ITIC. In both these cases, even though we increase the concentration of ITIC in the polymer matrix, still in S1 state, this is S1 state, it is more frontal excitons. That indicates that, and we also observe the same transport band gap and the exciton binding energy from the similar approach. So what is happening here, like not just molecular packing, it is important like how it packs. Because I already shown in the UV this like Y6 have different dimer configurations, right? So this different, it is also very important like how it packs. So the type of molecular packing actually determines the CT property. Next, we are going to see like how we can prove this more quantitatively. For that, we have the equation, EA equation, and we know the applied voltage thickness, we know. Then we can do fitting using the Gaussian band, first Gaussian band of the thin film absorbance. We use that data to do the fitting and extract the delta P and delta U values. And we can see this is the table which is showing the extracted delta U and delta P values. Here in ITIC, we can see the delta U values is around 7.92 and 7.58, pretty close, and it is more first derivative. Normally, our understanding is the larger CT means larger delta U, but here for 10% Y6, the value is around 9.7, bit larger than pure Y6, which is contradicting to our understanding. That's why we took the ratio. You can see for pure Y6, the ratio is pretty large. That indicates that for determining the CT property, along with delta U, we have to consider delta P as well. You can see for pure Y6, the delta U value is low. So we can say that pure Y6 has larger delta U by delta P ratio than diluted Y6 due to its distinctive molecular packing. So delta U by delta P is directly proportional to CT property. This is a small illustration to show the physical significance of delta U by delta P ratio. For the same dipole moment, the overlapping of electron and hole wave functions can decide the CT property, because the delta P, the change in polarizability, is actually related to the delocalization of wave functions. And there is already from some of the literature, like the Y6 have different dimer configuration, like core-to-core interactions, core-to-terminal interactions, and terminal-to-terminal interactions. In Y6, 45% of the formed dimers are actually terminal to terminal, and the rest of like around 20% is around CCTT and CT dimers. For different dimers, the electronic coupling and the delocalization will be different. But in ITAC, terminal to terminal interactions will be more. Maybe it is because of the steric effect or its molecular structure. So that's why we can conclude that Y6 have strong CT properties due to its distinctive molecular packing or these different dimer configurations. So coming to the conclusion, I think I have convinced you enough that electro-absorption spectroscopy is a technique which can give us more information about the delocalization, CT properties, molecular packing, binding energy, etc. And so we already showed that Y6 has strong molecular packing, and also it enhances the CT property of Y6. We used a polymer which can successfully control the molecular packing of Y6 and also ITIC. Then we extracted delta U and delta P to quantitatively explain the CT properties using the device absorbent derivatives. Then delta U by delta P ratio is more reliable than the absolute value of delta U to understand the CT properties of these non-fluid acceptors. We have to consider delta P, that is a very critical factor in determining CT property, as it is related to the overlapping of electron and hole wave functions. These results gives an insight into the better molecular design of novel acceptor materials by engineering the intermolecular interactions and the delocalization of wave functions. So that's all I wanted to share with you guys, so that Y6 have strong molecular packing and increased CT property. Coming to the acknowledgement, I would like to thank my supervisor, Dr. Stephen Sang. He's my greatest support. Dr. Liu Taili, he's actually trained me how to do the ES spectra and also develop the delta U by delta P ratio. My group mates are here: Sishin, Yusan, Constance, and Shanchao, Harry. And valuable contribution. Thank you, Professor Ip, for constantly supporting our group. Dr. Shenka Ichen, Dr. Philip Cho, Eskeso, and Dr. Jingdo Lu for their valuable contributions to this work. And I also wanted to thank the lab technicians in our physics and MSE lab. Thank you. Thanks for this opportunity. I'm very honored to have this opportunity. Thank you.